thanks for letting me talk here. This is about a project I started about 2 years ago with Bela Foxcamp and Bertrand Chaperon. The logo is currently a pickle on a surfboard, generated from a large language model, and the title is Particle-in-CelL for efficient Swell. And we submit this soon to James when we agree on a version. The reason why I started this is I really wonder how we do RC interaction in global eddy resolving models, right? You forgot the zoom. Oh, the whole screen, yeah. No, you have to find the window.
So did somebody switch to 2 screens? Is that now number 1 is number 2? I think that's what we did by mistake earlier. So which screen are you sitting on? Is it okay now? Is it okay now? I give up.
I don't speak French, so we leave it as it is, I guess. Okay, yeah, so I started this because I want to know how we do RC interaction in global eddy resolving models, right? We will have models that resolve the mesoscale very well, that some partly observe the model the sub-mesoscale, and the question is, what do we do with the RC interface and how we represent that? And since it's the WISE meeting, you are convinced we have to provide a non-equilibrium C state. That means we should model waves explicitly, right? For all these processes you study and like to study. And I just show you here 2 examples. One is the figure on the left that Bia showed yesterday. That is SWOT observations with mass on top of it. And you see the relatively small grains in HS. And the other example is the Martian ice dome problem. The orange area here around Antarctica illustrates the Martian ice dome. That is the area that is affected by waves. That means waves break the sea ice and therefore change fluxes pretty intensively. The problem is now that if you say these things are important, you must admit that we don't have the model infrastructure in place to do this in global coupled integrations, right? We currently cannot represent all these wave processes on the global scale and assess the impact on the large scale climate. The reasons for that I try to illustrate in the next 2 slides. This is a typical observation at Ocean Station Papa. You see here 3 wave systems. One is the wind sea, which is this big red blob, and 2 swell systems. And the variables you need to describe the system are pretty much 9, right? For each of them you need a peak frequency, a direction, and an energy, right? That gives you 9 variables. However, if you model that with a spectrum model, any spectrum model, you discretize in frequency and direction, and you have at least about 600 variables to do that, because at each of these black dots you solve the wave action equation and do all the machinery that we talk about since Monday, right? This is a conservative estimate, right? ECDWF runs way bigger systems, and the problem is now that the information that is used for coupling, that means that information that drives the parameterization, is only 1 to 3%, right? We're using 9 variables, maximum 9 variables to couple that, but we use about 600 variables at each grid point to actually get that information, right? That has bad consequences if you scale that up. This is a so-called weak scaling plot in a log-log scaling. This is the nominal resolution of your ocean model or of your wave model, and this is the computational power or the computational effort used per simulated year. Here I do some tests with WaveWatch where I use backbone like very simple switches that should be cheap. I don't have any I/O there. And you see there's roughly an n log n scaling. That means if I go from CMAP 5 resolution of about 1 degree to a quarter resolution degree, I will change my computation effort by 1 of magnitude. However, what is currently done in CSM is WaveWatch in 2 degrees, and then the effort is roughly here because of the switches they use and the I/O. If we now would extrapolate that to something we want to run, 10 kilometers, you need a computation effort that is about 3 orders of magnitude larger, right? And that will not happen simply because we don't have the computer for that, and we cannot justify the amount of information that is there to compute the wave state versus the amount of information that is used to drive the parameterization, right? So we have to ask if the increasing complexity or the increasing cost is justified for the physical gain, for the gain of physical representation, right? There's indefinitely a mismatch, and that's what we try to circumvent. So there's basically 3 choices then. A, we ignore what we know. We don't do the wave physics in there, and all parameterizations are functions of U10. B, you buy a bigger computer, and a few places in the world can do that. Or C, you can't do that as NSFN car right now. And so you have to come up with a different solution, right? You have to be smarter, and that's what we try to do here. So that's why I invented the 2nd generation plus model. It's called PiCLES, and it solves the wave action equation along Lagrangian trajectories, these blue lines here, and then regrids periodically. And each of these Lagrangian samples is a representative sample of the wave.
Allora qui subito lo vedi davanti, cosa dici? O lo vuoi qui? Che cosa?
Someone is speaking?
Okay, thanks. The main objective is here to trade accuracy for convenience, right? We will not be as accurate as WaveWatch, and we don't want to be because we don't want to predict waves. We want to model SC interaction. These are very different purposes. Yeah, we do that by reducing the high dimensionality of WaveWatch or of any spectrum model, and yeah, that will allow us to describe a sufficiently accurate C state. We do this fast by minimizing particle-particle interaction. We will have a very good performance on GPUs, and this is written in Julia because it's a pretty good language to do that. And we focus on open ocean waves because coastal problems are more complicated. All of this is done, of course, with having in mind that we want to have a better representation of the SC interface as a whole, and then there's more data, right? So actually, by explicitly resolving waves, we hope to move towards a better RC interface model that represents the physics better, but also enables things like a hybrid model. That means you tune this whole model on remote sensing data directly. So of course, I read the literature, and there other people have tried 2nd generation models before, right? So here in this line of complexity, so to say, we have 3rd generation models that came after Susan Hasselmann's 85 paper. And then there's these parametric simple models from John Schwab and similar level of complexity, right? They're just parametric functions. And there's something in between, which are these Lagrangian models, where you grow your wave action along a Lagrangian particle that follows the wave packet. And what we do something a bit between, right? We basically go back in the future. On purpose, we go before the innovation from the Hasselmanns and sit here. We do 2nd generation plus. That means we do this Lagrangian wave modeling, but we're adding a regridding term so that we actually resolve 2D space and time. That's what you want if you couple it to standard Eulerian systems. Okay, a few numeric slides, actually only 2. You start with the wave action equation. You do some math, you integrate in wave number space, you neglect currents, and we basically follow the formulation from Goodric's 21, but in Cartesian coordinates, and then we end up with the small system, the small ODE system that describes the log energy, the group velocity vector, and the direction, right? And that's the system we solve for each particle individually. Then there's source and sinks terms and coupling terms and so on. They look pretty similar as they would look in simple spectrum models, and that's it. That's my particle model. And this creates this particle state vector, as I said before. To make this work, we have to do one more step, right? And that's explained in this model algorithm. So we initialize at each corner point of this grid cell, that is, for example, an ocean grid cell, a particle, right? And then we let these particles grow given the winds they experience, right? And that leads to a deformation of the ocean grid, right? From T to T plus delta T, you're getting from this regular grid phase to a deformed grid. And what you then have to do, you have to remesh this deformed grid back to the Eulerian state. So you're here, and then you want to put this information back there. And that's where the particle-in-CelL paradigm comes in, where you use basically geometric weighting to get your information back here to these grid points. The problem is now that the state vector P is not additive, right? You should not add group velocity vectors. It doesn't really make much sense. But you can add energy and momentum, and that are the conserved quantities here. And that's what we do. So we do have a Lagrangian step where we deform the grid, then we map to this Q here, this vector, and then from Q in this space, we map to the Eulerian grid, and then we map back. So it's a triangular thing where we just iterate around and shift our physics in the coordinate system as we want to. That gives us some flexibility in where we represent the physics, right? So we can do fast physics like wave growth along the Lagrangian section, and slower physics like dispersion and current coupling, for example, on the Eulerian grid. And that keeps the whole thing relatively slick. Okay, then we do some accuracy tests. This is the non-dimensional fetch law. Basically, you know the gray curve, that's Pearson-Moskowitz. You know the red curve, that's for Donnellan et al., for example. And the other two lines are PiCLES. The blue line is PiCLES, and the green line behind that is actually PiCLES without regridding. So that's just the Lagrangian wave growth. And what you see is they're the same. That means that this remeshing algorithm is completely conservative. We do not have any dispersion there, and that's a very good characteristic to have for a numerical scheme. We can get a bit more complex. Here, winds blowing offshore from northwards on half of the domain, so this is X and this is Y. And as we grow in time, we grow waves. That looks okay. You do the same in WaveWatch. That looks the same. Instead, that WaveWatch is more diffusive, right? There's diffusion and dispersion going on, and my numerical scheme doesn't have that. We have not implemented that. But I show you this because I can control this very well, right? There's no numerical problem in the diffusion. The diffusion just comes to the amount I want to have it. I skip that. And then the question is, of course, what is with Swell? The model is so cheap that we actually can copy the whole model in a layering sense. That means the upper layer, which are illustrated by these blue dots here again, is susceptible to the winds. That's where we grow winds. And the lower layers will propagate swell, right? And as we know, swell is relatively unreactive to the wind system most of the time, right? And then you can change the complexity of the whole thing by adding more layers for each swell partition you want to model. And we think we're fine with 3 to 4 layers in total. This plot you've seen before, but now I added PiCLES to it. So I do here weak scaling tests with PiCLES. And you see that in all cases, doesn't matter if I run this on 2 degrees or a quarter degree, PiCLES is an order of magnitude faster than the cheapest version of WaveWatch, right? These are pretty old physics. And it's in fact about 4 orders of magnitude faster than any realization we have in CSM right now. Or in other words, I can give you wave information for a wind speed problem for the same computation costs for a 10 kilometer model as you would have for a 2 degree model in WaveWatch, right? These are very different speeds, and that will enable routinely coupling of wave models in Earth system models. We will implement that into CSM, and I don't explain the whole thing. I just want to show you what's roughly going on, right? So the different components of the coupled system, CAM and SICE and MOM, and then here's different wave models that we will implement. So there's WaveWatch, there's TheoWave, so that's just the parametric function of the wind speed, and then there's PiCLES in between. So this is basically a hierarchy of complexity of wave models, and they will all provide a similar vector of information per partition, so moments and group velocities and so on and so forth, and so on and so forth. And these will then be coupled to the different components, right? So we will unify how wave models speak to the other systems, and then you can choose the complexity you want to have of your wave representation. Okay, with this, I just repeat, I showed you a concept model of the second generation PLUS model for RC coupling. There's a lot to do, right? We have to deal with dispersion, diffusion, and refraction, right? We have to add more layers and make the thing more complex. And then there is the implementation challenge in CSM. So this is a Julia code that has to couple with Fortran through C. That's explicitly fun. And yeah, this also will enable, I think, a machine learning interface model, so to say. And with that, I'm happy to take questions.